In this video, we're going to look at solving different kinds of inequalities. So first, what is an inequality? Well, it's going to involve the use of the various symbols like less than, greater than, less than or equal to, greater than or equal to. And by solving an inequality, we are finding the set of numbers that make it a true statement. So as opposed to, say, if we had just a basic equation, like say x plus 3 equals 7, well, we only have one value of x that will make this true if x equals 4. Now if we made this an inequality, all right, if we did, say, x plus 3 greater than 7, all right, well, now we're saying what values make this true, because we went from having exactly one solution to having many solutions. X could be 5, 9, 11, so on and so forth. There's many different solutions in the case of this inequality. And when we solve an inequality, all of the values that satisfy it and make it a true statement, we call that the solution set. So let's look at interval notation next. An interval notation is just a nice way for us to represent the solution set of an inequality using either parentheses or using brackets, or it could be, you could have a combination of both. Parentheses and bracket, parentheses and a bracket. So this is what, when we get our solution set, we can then put it into, this is our writing it out in interval notation. And it'll just be a different way of saying the same thing. Because we can go from, if we had x greater than 5, right, and in interval notation, we would say 5 comma infinity symbol. So we're saying x has to be greater than 5. So our solution set that makes this statement, this inequality, true would be all values greater than 5, from 5 to infinity. Of course, not including 5, which is why it gets the parentheses, but don't worry about that quite yet. We'll get to those rules in a moment. But I just want you to see that this is putting it in interval notation when we're using the parentheses and brackets or one of each. And then finally, we can also visualize the solution set. All right, we can put things into a number line graph. So we'll keep our x greater than 5. All right, so we have our inequality here. And then we put it in interval notation. 5 comma infinity. This is our interval notation. We'll just abbreviate it. Right. And then another way we could say the same thing is by doing a number line graph. All right, we'll throw 5 right here. All right, so we're saying, and this will be an open circle, and again, we'll get to that momentarily. So we're saying all values that make it true will be going this way off to off to infinity if we kept going off to infinity on our number line graph. So we have a way to look at it from the inequality, x greater than 5, to interval notation, parentheses, 5 comma infinity, and then here on a number line graph. And these are all saying, it's just different ways of saying the exact same thing. All right, just different ways of saying the same thing. So let's go over now a couple specific rules you need to remember when writing out interval notation or drawing a number line. So when we're using parentheses, all right, when we have parentheses, that is equivalent to an open circle on a number line, and then that is also equivalent to, when we're looking at the actual inequality itself, less than or greater than. All right, so parentheses, open circle, and then just plain old less than or greater than. And this means, very important too, the endpoint, when we see it like this, the endpoint is not included. Right? Very important to remember when we have parentheses, like we saw in the last one, we had 5 comma infinity. Well, the inequality was x greater than 5, so x can't be 5. So that's why we use parentheses, because we're saying that the endpoint, in this case the 5, is not included in the solution set. And then if we were using brackets, that's equivalent to a filled in circle on the number line. And then that equates to less than or equal to, or greater than or equal to. So the key differences between these two here. And then, as I'm sure you can imagine, in this case, brackets, closed in circle, when we have the greater than or less than or equal to, the endpoint, we're saying it is included. Endpoint is included in the solution set. So key distinction here. So if we were given the inequality x greater than 12, right, in interval notation, it would be written, our solution set has to be, it'd be all values greater than 12, but not including 12. So that's why we would do parentheses. So 12 to infinity with parentheses, right? Because we can't include 12, because it's saying it has to be greater than. And then as a side note, when we're doing infinity, whether it's positive infinity or negative infinity, whenever we have infinity included in our interval notation, that always gets parentheses. Infinity always gets the parentheses. All right. So we have interval notation, and then if we did it on the number line, kind of similar to the last one we had. Put 12 there. So again, it's parentheses. So that means an open circle. All right, an open circle on the number line. And then we'd be shading off to the right, off towards infinity. So all of that would be included in our solution set. All right, so again, we have greater than, which equates to parentheses. And again, infinity always gets parentheses. And then on the number line, an open circle on the 12 because we're not including 12. Now be mindful, you may also see, depending on the textbook, you may also see number line graphs that are written with, just use the same one we had, that are written with parentheses and brackets. Oops, that'll be parentheses. So you'll see some that do it like that too, and then again, this would all be shaded. So they can be used interchangeably on the number line, whether you use the bracket and the parentheses or the circles. It's either or, but for our purposes, I'm going to keep sticking with using the circles. We're going to save the parentheses and brackets for interval notation, and then the circles for our number line graphs. Now let's go over a few examples just to drive home what we've learned so far. So if we had x less than or equal to -7, all right, so again, this is our inequality here. Now this time we have a less than symbol, so the infinity is going to be on the other side when we're doing the interval notation. And now sometimes we'll do it in this case here. Sometimes it may be helpful to draw the number line first, just so you can visualize it exactly. So if we have -7 and then just throw on a couple more just so we can really see it clearly. So we're saying x has to be less than or equal to -7. So we know we have the less than or equal to, so that equates to a closed circle because we can include -7. That would be included in our solution set. And then we'd be going off to the left now. This would all be shaded because it has to be less than or equal to -7. So this side of -7 would all be shaded. Imagine going off to, all of these are included in our solution set, going off all the way to -infinity in this case. So before we were going off, the first couple we were going off to the right, off to positive infinity, but now it's saying it has to be less than -7, so we're going off to the left, off towards -infinity. So in this case, our interval notation would be parentheses, because we're coming from -infinity, all right? Coming from -infinity, and again, infinity always gets parentheses, from -infinity to -7. And -7 is included, all right? Closed circle, less than or equal to, so that gets the bracket, right? So this is our solution set here. All values from -infinity to -7 would make this inequality true for us. And then we'll try, how about x about x greater than 3.5. It's a decimal there. X greater than 3.5. So we have our inequality. All right, and then we put it in interval notation. So it's just a plain old greater than, so that's parentheses, all right, because it wouldn't include 3.5. We can't have, obviously, 3.5 greater than 3.5. Well, that's not true. So 3.5 isn't included, so parentheses, 3.5, and then off to infinity. And then again, if we put that on our number line, all right, if we had 0 here, 3.5, okay. So we have parentheses, 3.5 is not included, so that's an open circle on the 3.5, and then we'd be shading off to the right, off to infinity. Now, what if we had something like, let's say, x less than 10, but also greater than 2. So x has to be greater than 2 and less than 10. So what values make this statement true? So in interval notation, we can still write it as parentheses 2 comma 10, okay? Because what we have here for our solution set, we have values that are in the middle there, sandwiched between 2 and 10. But again, parentheses, because we can't include 2 and 10. But of course, you might ask, well, why can't we say if we're not including that, why can't we do bracket and then just say 3 comma 9? And then we just cut out the 2 and the 10 because 3 and 9 are both included. Just do it like this instead. Well, we couldn't do it like that because then we're cutting out everything between 2 and 3. Because we're just saying x has to be greater than 2. So our solution set, we could have 2.01, we could have 2.5, 2.99. So that's why we can't do it like this. We'd have to do it like this with the parentheses from 2 to 10, but not including 2 and 10, because we could have, everything, a whole host of numbers between 2 and 3, just as long as it's greater than 2 is all. So that's why we have to do it like this. And now in this case, our number line would look like, again, we'll have an open circle on the 2 and the 10 because they're not included. And then our solution set would be all the values smack dab right in the middle of 2 and 10. All values in between there would make this inequality true. So just so you can see, one, where it's not always going off to infinity in either direction. And then how about x less than 15, and then greater than or equal to 7. All right, so now we have a less than and we have a greater than or equal to, so our interval notation is going to have a bracket and parentheses, so we have to be greater than or equal to 7. So on the left side, we're going to have bracket 7, because 7 would be included in our solution set, and then comma 15, but with the parentheses, because 15 would not be included. And then on our number line, so 7, we'll get the closed circle because it's included, and 15, the open circle, because it's not included. And then, like with the last one, all the values that make it true are sandwiched right in between those two values. So the inequality, the interval notation, and the line number graph, they're all different ways of saying the same thing for us. And let's briefly cover the difference between union and intersection in case you should see it. So, union, that symbol is just written as, that one's easy to remember, that's just written as U. Union equals a big U. So if we had, say, A union B, something like that. So what the union is telling us is the set of elements in set A, I've been talking about our what our solution set is, what makes it true, whatever A is, whatever B is. Solution set is the set of elements in set A, in set B, or it could be in both sets. So think of this one as, think of union as your OR operation. All right. So let's say our set A was parentheses 2 comma 5 union, and then our set B is 7 comma 10, and we'll say the 10 has a bracket, the 10 is included. Right. So if we were to graph this on a number line, so we have 2, 5, 7, and 10. All right, so let's start with set A. Let's get that graphed. So we have parentheses on the 2 and the 5, circle, and then everything in the middle will be shaded. And then we have, for set B, we have an open circle on the 7, and then closed circle on the 10 because of the bracket. And then again, everything in between is filled in. Okay, so we're saying by using the union, A union B, with this being our set for A and B, we're saying that it could be a solution set. It could be the elements here in set A. It could be the elements here in set B. Or it could be both sets. So if we write this out in interval notation, we have x has to be greater than 2, less than 5, or it could be we have x greater than 7 or less than or equal to 10, right? Because we're saying A union B. So again, think of this. When you see union, think of or. It could be A, or it could be set B. All right? So I want you to think of when you see union, think of that as your OR operation for the values that make the inequality true. And now let's compare that to what's called the intersection. And the symbol for that is upside down U. All right, so if we had that written as A intersection B. So for an intersection, this is going to be our, remember it as your AND operation. So our solution set is the set of elements that are common to both set A and set B. All right, so it's no longer an or, it's an and. We're looking for where there's overlap, what set A and set B have in common. So if we were given, if set A was -2, 4, and then intersection, this will be our set B, 0, 7. All right. So if we throw this on the number line, so we have -2, and then just throw in 0, and then we have 4, and then we have 7. All right, so let's start with set A. So we have a parentheses on the -2. So that gets the open circle. That is not included in our solution set. And then we have a bracket on the 4. So closed circle, 4 is included. So from -2 to 4 for set A. All right, so that's the solution set for set A. Now for set B, we'll do that blue. So set B is, we have a bracket on 0. Let's get a closed circle. And then parentheses on 7. So that'll get our open circle. So from 0 to 7, this is our set B here. Now look at where, yeah, we'll do this one in well, we'll do in yellow. All right. So here, notice where we have the overlap, where they have it in common, from 0 to 4. From 0 to 4 is where the solution set, where we have the same values common to both set A and set B, which is what we're looking for in an intersection, the and, all right, where they have overlap, where they have, like I said earlier, the set of elements are common to both A and B. So in this case, our solution set would be for A intersection B, right? Answer to this would be, we'd have, and there's an open, or sorry, a closed circle on the 0, so that gets a bracket. So we have 0, comma, and then again we have a closed circle on the 4, so that gets a bracket as well. So our answer for that, when we're talking about intersection, is bracket 0, 4, right? That's what they have in common. So again, when you see union, think or, think they'll be going off in different directions. And then if you see intersection, think and, think what they have in common. It's going to be sandwiched between two numbers on the number line. Now let's look at solving some linear inequalities first. All right, now that we have a baseline for what an inequality is and closed versus open circle brackets, and parentheses, union, intersection. Now that we have a good baseline, let's look at solving a linear inequality. And a linear inequality, which for us will just be in terms of one variable, x, is one that can be written in the form ax plus b, and then we'll have 0 on the right side, and then it's just a matter of whether we have less than, greater than, less than or equal, greater than or equal to. But what it has, a linear inequality has in common, it just has the ax plus b form on the left and then 0 on the right. And that's just a matter of whatever symbol we have in the middle between them. And a very important note going forward, another very key rule to remember, whenever you multiply or divide both sides of an inequality by a negative number, right? So whenever we're multiplying or dividing by a negative number, the direction of the inequality symbol is reversed, right? So if you multiply or divide by a negative number, then you switch your sign around. So if we had less than or equal to, right, we would then have to change that to a greater than or equal to. Or if we had a greater than, that would be switched to a less than. All right? So a very key point to not forget, if we multiply or divide by a negative number, the inequality symbol is reversed. So the key for solving a linear inequality like this, in this form, is simply to isolate the variable on one side of the inequality sign. So let's do, as our example, if we had 3x less than 9x plus 4. All right, so let's work on isolating the variable. So let's move the 9x over. So 3 minus 9, so we'll be at negative 6x less than 4. And then we can divide by the negative 6 to get x by itself. And like we just talked about here, this is where we would remember the rule we just talked about. So we divided by negative 6. So now we just have x left over. But since we did that, now we have to reverse the sign. So now it becomes, instead of less than, now we have to have greater than. And then we'd still have over here negative 4, 6. So we switch the sign because we divided by the negative. So now we have x greater than negative 4, 6, which could be simplified to just negative 2/3. So we have x greater than negative 2/3 for our answer. And now let's put this in interval notation. We just have a simple greater than, so we're going to be working with, we'll have a parentheses, so it has to be greater than negative 2/3. So we'll have negative 2/3 and then off to infinity, which always gets the parentheses. And if we throw this on the number line, so we have our negative 2/3 here, and then maybe zeros right here. So we'll have an open circle, and then everything off to the right will be shaded off to infinity. Right, so that's our answer for that one. So linear equalities, those aren't too bad. But let's look at a compound inequality. Let's suppose we had two separate inequalities. All right, let's say we had -3 less than 2x plus 1, and we had 2x plus 1 less than or equal to 3. So notice how they both have the 2x plus 1 in common. So these could just be expressed as a single compound inequality with 2x plus 1 in the middle. So we're saying 2x plus 1 has to be less than or equal to 3, but also greater than -3. All right, so here we have a compound inequality. All right, we have pieces on both sides of our variable. So our goal is still, we just want to get x isolated, but this time it'll just be left here in the middle. And then with a compound inequality like this, when you're solving it out, you want to make sure that you do the same thing to both sides. So if we're isolating x, obviously we'll get rid of this 1 first. So we need to make sure we subtract 1 from both sides of this inequality. So we'll have 2x and then less than or equal to 3 minus 1, 2, and then greater than -3 minus 1 be -4. All right, and then all we have left to isolate the x is to divide by 2, and we have to do it to both sides. So we're left with x less than or equal to 1, and then greater than -2. All right, so this is our answer. This is our solution set when we solve out this compound inequality here. X has to be greater than -2, but less than or equal to 1. So in a solution set, we would say, in putting it in interval notation, so we have parentheses -2 and then 1 for that one. And let's take a look at one more of the compound inequalities. So let's do 8 less than or equal to, we have 5/7 x plus 3 less than 13. All right, so like we started the last one with, let's subtract the 3 out, and we have to do it both sides. So 5, and then just say x, and then 10. So now let's clear that fraction out, get x by itself. And all we have to do in this case is, if we were trying to get rid of 5/7, how would we do that? We can just take it times its reciprocal. Take 5/7 and multiply it times its reciprocal, 7/5. Everything will cancel out, and then we'll just have x by itself. But we'll need to do it times everything, so I'm just going to put giant parentheses, and then taking everything times 7/5. All right, so when we do that, we'll just have x left in the middle, and then over here we're taking 7/5 times, be like saying 5/1, and then we just multiply straight across. 7 times 5 is 35. And then on the bottom we have 5 times 1 is 5. So 35 divided by 5 is just 7. Then over here we'd have 10 times 7/5. So we have 70 divided by 5, which is, so will be less than, that would be 14. So we have x has to be greater than or equal to 7 and less than 14. So interval notation, we would have a bracket on 7 and then parentheses 14. Can do it on this one. If we do the number line, so it looks like we'll have a closed circle on the 7 and an open circle on the 14 because that is not included in our solution set, and everything in the middle will make the inequality true. Now let's look at solving inequalities with an absolute value. So first, what does an absolute value tell us? It tells us the distance of a number from 0 on a number line, regardless of direction. Right? It's always a positive number, 0, since you can't have negative distance. Hence why if we take the absolute value of -3, that just becomes +3. All right. So absolute value, we're looking at the distance, how many units something is from 0 on the number line. So for instance, if we had absolute value of x less than 5. So what this is telling us is the distance of x from 0 is less than 5. So which numbers are fewer than 5 units away from 0? And of course we have to remember to take the negative side into account too. So we'd have to be between -5 and 5. Right? Well, less than. So everything from, if we write this out, x would have to be less than 5, but greater than -5 in this case. All right, that would get us, because we're not including, obviously, we're not including -5 and 5, but everything in between those values would get us fewer than 5 units away from 0, which would satisfy what we're looking for, absolute value of x less than 5. All right. So emphasis on the and here when I said x must be greater than -5, and it also has to be less than 5. So emphasis on the and there, because I like to remember, if it's helpful, think of this as a less than. All right, think of when you see this absolute value of x less than 5, think of it as a less than. All right, it's going to be an and. We're going to have our solution set will be sandwiched between 2 points. All right, on a number line, because if we graph this, we'll have -5, 5, and then we're saying it has to be less than 5, but greater than -5. All right, so everything in between here, the -5 and the 5, not including those values, will get us just what we're looking for, fewer than 5 units away from 0, because we're talking absolute value. All right? So when you see less than, think less than, all right? And we're going to have it sandwiched between two values, as opposed to if we stick with the same absolute value x, but this time if we do absolute value x greater than 5, all right, so now we're saying the distance of x from 0 has to be more than 5, so x could be greater than 5, or x could be less than -5. Because we could have 6, that would work. We could have -6, that would work too. Both of those are greater than 5 units away from 0. So in this case, when we see a greater than symbol, I want you to think great or, all right? You'll have an or. Right? The solutions are going to go outward in two directions, all right? So if we put this on a number line, so we have absolute value x greater than 5, all right? So we're saying that we'd have -5 and 5, all right? So we're saying x must be greater than 5, or x could be less than -5, right? Again, it wouldn't be included because it's not a greater than or equal. So we'd be going off in this direction. Those would all be true. Or we'd be going off in this direction. Those would all be true as well. All right, sorry, I put the circle there. Open circle. All right, so great or, think or, and you'll be going off in two different directions. All right, the less than and, all right, and you'd have something like this, all right, and less than, all right, sandwich between 2 points, and a great or going off in two different directions. X less than -5 or x greater than 5, okay? So less than, great or, right? If you can remember that, that could be useful for remembering, like especially remembering what your number line will look like. So let's take a look at this example here. So absolute value, x minus 1, plus 5, less than or equal to 13. All right, so let's get the 5 out of there, and let's work on getting things isolated. So now we have absolute value x minus 1, less than or equal to 8. All right, so now let's apply what we were just talking about. So now this is a less than, so a less than. Okay, so let's keep that in mind. It's a less than an and. So we should have our solution set should be values that are between 2 points here. So now if we write this out, a less than, so we're saying x minus 1 has to be less than or equal to 8 and greater than or equal to -8. And then we can isolate the x, again, do it to both sides. So we end up with x less than or equal to 9, and it has to be greater than or equal to -7. All right, so less than. So it kind of turns out it ends up just like our number line we see it sandwiched between 2 points. When we write it out, the inequality, it ends up looking like one of our compound inequalities, like we worked on earlier. All right, so we have bracket -7 comma 9 in our solution set. So if we draw that out, we have from -7 to 9, and everything gets the closed circle because -7 is included and 9 is included, and then it'll be everything in between in our solution set. All right, so we're saying x has to be less than or equal to 9 and greater than or equal to -7. All right. And worst case, we can always go back and, if we're ever unsure, we can always go back and check our work. As we know, if we plugged in -7, -7 minus 1 is -8, and then the absolute value, so that becomes +8. 8 plus 5, it's equal to 13, so that works. And then 9 minus 1, again, 8 plus 5 equals 13, so that works as well. So that is our answer for that one when we solve that out. And then let's try one more. As I'm sure you can imagine, this will be a greater than, just so we see an example of that too. If we had 5 plus 1 minus x over 2, and that's in the absolute value, greater than or equal to 8. All right, let's take care of the 5 first. So we end up with absolute value 1 minus x over 2 greater than or equal to 3. Okay. All right, so we got the absolute value by itself at least. So we have a greater than, so a greater. Right. So an or, so think of it like we can split this into 2 parts here. So we're saying that 1 minus x over 2 has to be greater than or equal to 3, or 1 minus x over 2 has to be less than or equal to -3. All right, it's an or. All right, we're going to be going on the number line, we'll be going off in opposite directions. All right, so if we solve, now if we actually solve for x, so let's subtract the 1 over. So we'll have negative x over 2 greater than or equal to, oops, sorry, that should be a 1. So greater than or equal to 2. Too much. X over 2 greater than or equal to, this is a -1, so this is 2. Apologies for that. All right, so now get x by itself. We can multiply out by 2, and I would just do times -2. All right, that way we can get rid of the 2 and get rid of the negative. So just what we want, we'll have just x by itself. So I would multiply both sides times -2. Okay, so this all cancels out, so we just have x left over. And then don't forget our rule here, because we multiplied by a negative, so we need to reverse the sign. So this now becomes less than or equal to, and 2 times negative 2 will be negative 4. So we have x less than or equal to negative 4. All right, or, and then if we do the same thing over here, minus the 1, negative x over 2, less than or equal to negative 3 minus 1, negative 4, and then do the same thing, negative 2, both sides, and we're multiplying by a negative, so sign gets reversed, so less than or equal to becomes greater than or equal to, and this would become a positive 8. All right, so we're saying x has to be less than or equal to negative 4. Right, so that'll be going off to the left on the number line, or x has to be greater than or equal to 8. So that'll be going off to the right on the number line. So still going in opposite directions because we did, make sure. That's why you have to be careful remembering the rule. Don't forget to do it, because if we miss doing it on one side, then everything would be off. But we remember to reverse the sign on both sides, so we're still going in opposite directions, just like we should see for this type, the great or. So we'll write out our interval notation. So we'll have negative infinity, and then negative 4, and that gets a bracket. And then this will be a union, because remember, union, think of that as your or. Right? Think of union as your or. And then we have bracket 8 off to positive infinity. Draw out our number line. All right, so negative 4, that gets the closed circle. And then we'll be shaded off to the left, going towards negative infinity. And then 8 also gets the closed-in circle, and that's going off towards the right, towards positive infinity. So great or, so it'll be going in opposite directions. And now I want to look at one more item. If we were asked to solve a nonlinear inequality, because we did linear when it's in that general form, the ax plus b, and then whatever inequality symbol, and then 0 on the right side. A nonlinear, like say quadratic inequality, just so we can see one of those too. If we had x squared less than or equal to 5x minus 6. All right, so first step is going to be kind of like the general form we had with the linear inequality. Our first step is going to be moving all the terms to one side, because I still want to get 0 on one side of this inequality. So if we subtract the 5x over and add the 6x, if we move both of those over to the left side, so we'd have x squared minus 5x plus 6, and then we have less than or equal to, so now we just have 0 left over on the right. Right, so first step, get all the terms moved to one side. And then second step is just going to be get it factored. So we'll need factors of 6 that add to negative 5. So we're going to have to do a double negative. So let's do 3 and 2. That should work for us. So x minus 2 times x minus 3 less than or equal to 0. And now our third step is going to be find the zeros and put them on the number line. All right. So find our zeros and then number line. Right. So if we did like we've seen way back, we can still take and set each one. If we just set it and pretend that's an equal, set it equal to 0. We just want to know, like just like when we had an equation, set it equal to 0 is all we're doing. So don't let the inequality, the less than or equal to, confuse you. Still just figure out what our zeros are. Right? Because that's what we're going to put, as you'll see, we're going to put that on the number line. So x would be equal to, that would be 2, and x would be equal to 3. So those are our zeros, right? And put those on the number line. So we have 2 and we have 3, okay? So now our next step is going to be, we need to choose test values. And by test value, I want a value. If you look here on our number line, we have 3 intervals. We have 2 off to negative infinity. We have an interval here. From 2 to 3, we have an interval there. And then from 3 to infinity, we have another interval there. So we have 3 separate intervals that we're looking at here. So for test value, what I mean is we need a value in each interval. So let's do, for this interval, let's just do, whenever you can do 0, that's an easy one to do. Just pick 0 as a test value. All right, so we'll do 0 for that interval. And then our test value in here, so we need between 2 and 3, we'll probably just do 2.5. And then here, our test value, let's just do 4. All right, so now that we have our test values, our next step is going to be plugging those test values into the original inequality. All right, so plug your test values into the original inequality, and we'll rewrite that here. Make sure we can still see our test values. Okay. So our original inequality was, we had, well, we'll do it after we had moved the terms over, obviously. So we'll have x squared minus 5x plus 6 less than or equal to 0. Okay, so that was just after we moved the terms to one side. But this is our original inequality here. So now we're going to take each of these test values and we're going to plug them in for x, and we're going to see whether they come out true or not. Space, so I can see my number line. All right, so if we plug in 0, that's our test value, the first one. So we'd have 0 squared minus 5 times 0 plus 6, which is, that would be 0 minus 0 plus 6. So that would just be equal to 6. And 6, is that less than or equal to 0? That would be a definite no. So what that tells us is this interval here, space, all right, this interval here, this interval 1, so that is false, right? We would say that interval is false, that is not true. So now let's try the middle interval with our 2.5. All right, so we have 2.5 squared minus 5 times 2.5 plus 6, and that is equal to negative 0.25. Okay, so is negative 0.25, is that less than or equal to 0? Well, that would be true. Okay. Not very much. It is. So that is true. So interval 2 is true for us. And now let's do our last, let's do our last interval here with 4. So we have 4 squared, that's 16, minus 5 times 4, so 16 minus 20, plus 6, so that gets us to 2. So we have 16 minus 20, or, yep, 16 minus 20, so that's negative 4, plus 6 is positive 2. Well, is 2 less than or equal to 0? That is also not true. So interval 3 here, we would say, is not true. So in this case, based on what we just did by plugging the test values in, all right, our only interval where we said it was true, where it actually worked in the original equation, was the second interval from 2 to 3. So we would write that out as, we'll write out our interval notation. So we would say bracket 2 and then bracket 3. Right? We're saying that x has to be less than or equal to 3 and then greater than or equal to 2. All right, because again, this was, if you look back here, that was the only, when we plugged in our test values, that allowed us to determine whether those particular intervals were true or false, whether they would be part of the solution set. And the only part that was true was the middle one from 2 to 3. So that is the only answer that is part of our solution set. And we can always check our work too if we plug in. If we plug in here, I guess obviously it never hurts to check just to be safe whether you should do parentheses or brackets. If we plug in 2, we have 2 squared is 4, 4 minus 10, so that's negative 6 plus 6 would be 0. So, and we can be less than or equal to 0, so 2 would be included, that is true. So we get the bracket on 2, and then if we do 3, 3 squared is 9, 9 minus 15, that's negative 6 plus 6. So again, we get 0, so that is true as well. So that's why we can always check to be safe, but 2 and 3 would be included. So that's why we get the bracket on those. All right, and I think we will stop there for this lesson. I think that's enough of the inequalities for now. All right, so hope this lesson was helpful, and thank you for watching. And of course, be sure to check out the channel for more algebra lessons as they come up.